All right, let's work through this problem somebody posted a question about on Piazza, and this is a fairly involved problem that combines rotational dynamics and linear dynamics. It's technically a chapter 7 problem, but it ties together everything we've done having to do with forces and rotational motion and torques. So the rotational version of forces and the rotational version of Newton's second law. I've gone ahead and started this video off with the problem outlined. There's a rope over a pulley, and the pulley is free to rotate without friction, but the rope does not slide over the pulley. The key thing about that is that that means that the tension in the rope is different on either side of the pulley. Normally, if you've just got two people pulling on a rope, the tension is the same everywhere in the rope. Or if you've got a rope going over what was called an ideal pulley, which meant that it was massless, then the tension on either side is the same. So we had some example problems where there was a rope attached to a block, and the rope goes over a pulley to another block that's pulling down on it, and the tension was the same in both cases. But in this case, the problem is specifying that it is not an ideal pulley. The pulley has friction. The rope doesn't slide on the pulley, so there's different tensions on either side. And the question is just, we got this rope over the pulley, there's two masses on it. What is the acceleration of the system? How do the masses move? How do they accelerate? So the key thing to identify here first is that you have different tensions on either side. And second, that the acceleration of those two objects is the same because they're physically tied together by that rope. So whatever the acceleration down is of m2, that's got to be equal to the acceleration up of m1. And in turn, that acceleration is the tangential acceleration of the rim of the pulley. So how do we approach this problem? We're given the masses of the two masses that are indicated here. We're given the mass of the pulley and the radius of the pulley. So how do we approach this? What makes it turn? Well, it's a force that's making it turn, so we need to do free body diagram. So let's start with a free body diagram of mass m1. So do it our old-fashioned way. Mass m1 becomes a dot. I'm going to play around with my fancy colors here so I can draw my force vectors the way they do in the book. So there's a tension upwards on mass m1, which I'm going to call T1. And there's the weight down, W1, which is just equal to m1 times g. So that's the free body diagram for mass 1, but remember that with the free body diagram we also need to label if there's anything we know about the acceleration or the velocity. And since m2 is 4.5 kilograms and m1 is only 2 kilograms, m2 is winning the battle between those two things, winning the tug of war. So m2 is going to go down, m1 is going to go up, which means the acceleration for this object is up. Now we can write Newton's second law for m1. The sum of the forces equals m1 times a. And I did not put a 1 subscript on that acceleration because that is the acceleration of everything in the system. They're all tied together. They all have the same acceleration. Well, let's stick with our normal convention that up is positive and down is negative. So the sum of the forces here, T1 up minus m1 times g equals m1 times a. So that gives us everything we can or need to know about m1 from Newton's second law. Now let's do the same thing. I'm going to go ahead to the next page for m2. Free body diagram of m2. That's also just a dot. We'll also do our fancy red vectors here. Its weight down, W2 is equal to m2 times g. And there's a tension force in a rope upwards on it, and I'm going to label that T2. Again, because since the pulley is not ideal, the tension is not the same on either side of the pulley. So I have to allow that to have a different value. And in this case, we know that since m2 is bigger than m1, this accelerates down. So there's the acceleration. And Newton's second law for m2 looks like this. T2 positive up minus m2g down is equal to minus m2 times a. A is down, that gets a minus sign. So now I've got two equations, but I have three unknowns. I don't know a, I don't know t1, and I don't know t2. But there's another piece of this puzzle, and that is the pulley. So I'm going to make something that I'm going to call a torque body diagram. I don't know if that makes any sense. It's still just as much of a free body diagram as the other, but it's to illustrate torques on a finite sized object. So instead of our object becoming a dot, we have to actually draw the thing. Here's our wheel. It is free to rotate. It's got, from the wheel's perspective, it has, oh, I should have done this. Let me do this in my fancy red. From the wheel's perspective, there's a rope T1 pulling down on it, and then there's another rope on the other side, T2, pulling down in the opposite direction. And we were given the radius of that pulley, RP, and if you've got a round thing and you have a rope coming on it, wherever the rope stops its connection with that pulley, it's going to be perpendicular to the radius as I've drawn here. And so the torque due to each of these forces is just the force times the radius. So remember which way things are rotating. Because m2 is bigger, it's actually going to be rotating this way. So the angular acceleration of the pulley is clockwise. Clockwise means negative, and counterclockwise is positive. So let's take a look at Newton's second law for rotational motion. It's the sum of the torques is equal to I, the moment of inertia, times alpha. So that's just exactly analogous to what we had with the free body diagrams for the two objects. The sum of the forces is m times a. Here, the sum of the torques is I times alpha. How many torques do we have acting on this? Just two. The one due to T1 and the one due to T2. Well, the torque due to T1 would make that thing want to rotate counterclockwise. So that is a positive torque. And that torque is T1 times RP. The torque due to T2 would make it rotate clockwise, which is negative. So that becomes minus, and that torque is T2 times RP. And that's equal to the moment of inertia of the disk of the pulley times alpha. And alpha, since the thing is moving in that clockwise direction, that gets a minus sign too. It's equal to minus I times alpha. I for a disk is 1/2 mr squared. You don't need to remember that 1/2 prefix. It's a different prefix depending on what type of object you're looking at. If it's a ring, it's just mr squared. If it's a disk, it's 1/2 mr squared. If it's a sphere or a hollow sphere, those coefficients are different. You do need to know, though, that it's always proportional to the mass. It's always proportional to the square of some length scale associated with that object. So let's go ahead and substitute that in. But first, we want to change that rotational acceleration. That's the rotational acceleration of the disk to the tangential acceleration, how fast in a linear direction a point on the edge of the disk is moving. And the relationship between angular acceleration and rotational acceleration, angular acceleration and linear acceleration is simply that the linear acceleration, I'll put a little t for tangential there, is just the angular acceleration times r. And in this case, that r is rp, and the tangential acceleration of that rope, in this case, is the acceleration of the things attached to the rope, which we're just calling A. So that means alpha is A over RP. So now let's go and rewrite this torque equation, Newton's second law for torques, where we had T1 RP minus T2 RP is minus I times alpha. That becomes T1 RP minus T2 RP is minus 1/2 MP RP squared. That's the moment of inertia, times alpha, but alpha is just A over RP. Now a beautiful thing happens, which is I've got an RP in each term on the left-hand side of this equation, and I have an RP squared over RP, which is just RP on the right-hand side, which means all my RPs cancel. This is one more example of why it is generally easier to wait until the very end before you put numbers in. I know it's super tempting. You've got the mass of the pulley, you've got the radius of the pulley, you have an equation for the moment of inertia, you want to get that number, so you've just got that number straight. Once you've written that number down, though, it's easy to forget what you put into it, and therefore it's easy to make a mistake by redoing a calculation or putting something in there again. It's much better to do everything symbolically until the very end of the problem and then put in the numbers that you need. So the RPs cancel, so we get T1 minus T2 is minus 1/2 MP times A. So that's what Newton's second law for the rotational motion of the pulley gives us. And our first two equations were T1 minus M1G is M1 times A, and T2 minus M2 times G is equal to minus M2 times A. So now I have three equations with three unknowns, T1, T2, and TA. I'm basically done with the physics. I have to do some math, and then I have to do a sanity check to make sure I didn't make any mistakes, because it's very easy with the signs to mess this up. That's a mistake I make in these kinds of problems all the time. So it's very important to do a sanity check at the end. Well, the problem is asking us for A, the acceleration. So what I'm going to do is take this top equation, I'm going to replace the T1 and the T2 in it from these equations 2 and 3. So let's just show how that looks. T1 from this equation is M1 times A plus G. That makes sense. It's accelerating upwards, so the tension in it has to be bigger than mg. It's bigger by the amount that it's the force required to accelerate it upwards, ma. For T2, we get T2 is m2 times g minus a, and that's less than the weight of T2, and that makes sense because the weight is winning out over the tension. M2 is going down, so that makes sense. Now let's substitute those guys in back into this equation. And what do we get? T1 is, oopsie, M1 times A plus G minus T2, which is so minus M2 times G minus A, equals minus 1/2 MP times A. If I'm solving for A, I want to collect all the terms with the A's on one side. So I've got here M1A plus M1G minus M2G plus M2A, minus times a minus is a plus 1/2 MP times A equals 0. I'm going to put the G terms on the other side and collect my A's. I have on the left A times M1 plus M2, Just highlight these. Here's my A terms, and here are my G terms. So my A terms put together have A times M1 plus M2 plus 1/2 times MP equals, when I put those two G terms on the other side, that becomes G times M2 minus M1. The signs change when I put them on the other side. That then gives me my answer. A equals M2 minus M1 divided by M1 plus M2 plus 1/2 MP all times G. And then I can put my numbers in and get them. But before I do that, let's take a look at this and make sure that it passes the sanity check. Suppose M1 equaled M2. What should the acceleration be? Well, if I've got equal masses on either side of that pulley, it shouldn't move, so the acceleration would be 0. And if M1 equals M2, I can see that in fact this equation would give me 0. So that's a good sanity check passed. As if M1 is 0, so there's no mass on the left, and if there's no mass in the pulley, then what should the acceleration be? Well, then M2 would just fall at free fall, so it would just be G. Well, if M1 is 0, this would be M2 in the numerator, and in the denominator, it would also be M2 if these other two masses were 0. M2 over 2 would be 1, and I would get acceleration equals G. So that's a couple of sanity checks you can do to make sure you've got this right. It's easy to make mistakes on this stuff, plus and minus business. So it's always good to do those sanity checks. We can go ahead and put our numbers in for this one. For M2, we had 4.5, and M1 we had 2. So we had 4.5 minus 2 divided by 4.5 plus 2 plus 1.5. Whoopsie. Times 9.8, and that gives me 2.5 divided by 8 times 9.8, or A equals 3.06 meters per second squared. That's the number. It's less than G. That makes sense. It's got to be because there's a weight retarding how it moves. So this problem combines pretty much everything we've learned from chapters 3 through 7. You won't see a problem this involved on your exams, but you will see material like parts of this problem on exams, or simplified versions of this on exams, and going forward if you're taking MCAT and things like that. So it's a really good problem that combines a lot of the different stuff that we've worked through and a lot of the problem solving strategies, the importance of setting up your free body diagrams, the importance of going through Newton's second law for every object that's got mass and doing it that way.